Welcome to this explainer. I want you to think about three wildly different things for just a second. The incredibly explosive liquid hydrogen rocket fuel launching a space shuttle, the slow brown flaking of rust on an old iron gate, and the sudden fizzing bubbles when you mix baking soda and vinegar in your kitchen. So, what do they all have in common? Well, they are all simply atoms rearranging themselves. Now, a lot of people think chemistry is just endless rote memorization, but as an educator, I'm here to tell you that it's actually a beautifully logical, predictable language. Once you know the alphabet and the grammar, you can literally read the universe.
Here is our agenda for today. 1. The building blocks of matter. 2. Spotting a chemical change. 3. The rules of reaction. 4. The grammar of naming. And 5. Same atoms, different structures. And let me reassure you right now, if you know how to add, subtract, multiply, and divide, you already have all the math skills you need to follow along. We're simply going to build the logic together.
Okay, let's jump right into section 1, the building blocks of matter.
To speak the language of chemistry, you've got to know its letters. These are the atoms, those elements you see on the periodic table. If you break matter down far enough, atoms are the smallest units that still hold a unique identity and specific properties. For example, oxygen is an odorless gas we breathe. Pure sodium, on the other hand, is a highly reactive metal that will spontaneously burst into flames if you just drop it in a bucket of water. Every single letter has its own very distinct personality. Now, what happens when we string these letters together? We get the words of chemistry, molecules. And honestly, this is where the magic happens. When elements chemically bind, the new molecule has completely different properties than its ingredients. Take hydrogen, a highly explosive gas, and oxygen, the gas that literally fuels a fire. Bind them together, and you get water, a liquid that actually puts out fires. The new structure totally overrides the original properties. And this brilliantly illustrates a vital distinction. Just putting two things in the same space doesn't automatically make a molecule. If you dump sand into a glass of water and stir, that's just a mixture. There's no chemical reaction happening there. The sand just settles right to the bottom. But in a compound, the electrons actually rearrange and bind. It's kind of like the difference between standing next to someone in an elevator and actually holding their hand. Moving right along to section 2, spotting a chemical change. So how exactly do we know when these molecules actually rearrange to form something new? Well, we have to differentiate between physical and chemical changes. A physical change is temporary, like melting ice into water. It's still H2O, just in a different state. But a chemical change alters the fundamental composition permanently. Think about burning a piece of wood. The oxygen in the air reacts with the carbon in the wood to yield smoke, heat, and carbon dioxide. You can't exactly cool that smoke down and get your log back, right? Because we literally can't see atoms with our naked eyes, we rely on observable clues to tell us a reaction has happened. Sometimes a solid turns into a liquid. Sometimes there's a dramatic change in color, like when an iron nail is dipped into a bright blue copper sulfate solution and the liquid slowly turns pale green as the iron reacts. Or you might see the evolution of a gas, just like the bubbling carbon dioxide produced when you mix baking soda and vinegar.
All right, section 3, the rules of reaction. Now that we can spot a reaction, we need to understand the unbreakable mathematical grammar that governs it. The absolute bedrock here is the law of conservation of mass. In chemistry, the universe keeps strict accounting. You cannot conjure matter out of thin air, and you definitely cannot make it disappear. If you have exactly 100 grams of reactants going into a reaction, you absolutely must have exactly 100 grams of products coming out. The mass simply changes form.
And because these atoms rearrange so predictably, they also bind in perfectly consistent mathematical proportions. If you take carbon and oxygen and form carbon dioxide, the ratio by weight of the carbon to the oxygen will always be exactly 3:8. It doesn't matter if that CO2 was made in a laboratory or exhaled from your own lungs. The formula is purely logical and completely fixed. To obey this fundamental law of the universe, we always balance our chemical equations algebraically. If you start with 4 hydrogen atoms on the left side of your equation, you must find 4 hydrogen atoms on the right side. It's not magic, it's just making sure the math adds up. Next up, section 4, the grammar of naming. Since there are literally millions of possible organic compounds, organic chemistry requires a highly systematic grammatical rulebook driven by the IUPAC naming system. You can think of this like a giant logical puzzle. Any complex organic molecule in the world can be named just by plugging pieces into this precise 5-part structure. You figure out your branches, check if it's a ring, Count your main carbons, look at the bonds, and identify the main functional group. We solve the puzzle by following a strict, step-by-step logic. First, the main functional group dictates the core name. Then, you find the longest continuous carbon chain. Next, you number that chain so your branches get the lowest possible numbers. And finally, if you have multiple branches, like a methyl and an ethyl, you simply list them in alphabetical order. Boom, no endless memorization required.
But wait, what happens if you have two different functional groups in the exact same molecule? Well, just like in any grammatical system, there is a strict hierarchy of importance. Carboxylic acids rule the absolute top of this list. If a carboxylic acid is present, it claims the suffix of the name and forces any other group, like an alcohol, to be demoted to acting as a mere prefix. Finally, let's bring it all home with Section 5, same atoms, different structures. We understand the rules and grammar, so let's look at the beautiful nuances. What happens when molecules share the exact same formula but have different layouts? We call these isomers. Imagine taking a box of Lego bricks. You can build a house, or you can take those exact same bricks and build a car. It's the exact same amount of plastic, but fundamentally different structures. In chemistry, simply rearranging the carbon chain yields entirely distinct physical and chemical properties.
There are a few ways these atomic Legos can be rearranged. You could have a chain isomer, where you take a long 5-carbon chain and snap a piece off to make a shorter 4-carbon chain with a branch. Or you could have a position isomer, where you just slide a functional group from carbon number 2 down to carbon number 3. Or, amazingly, you can have a functional isomer, where rearranging the exact same identical atoms completely converts a molecule from an alcohol into an ether. It's absolutely wild.
Now, look closely at the geometrical isomerism here. Sometimes the atoms are connected in the exact same order, but because carbon double bonds can't freely rotate, the 3D orientation really matters. If two chemical groups are locked on the same side of a double bond, it's called a cis isomer. If you just flip one to the opposite side, it's a trans isomer. Even this tiny, seemingly insignificant spatial flip totally alters how the molecule behaves and interacts with the world. And that brings us full circle. From the intense thrust of rocket fuel to the slow decay of rust, the universe is not just acting randomly, it's operating on the beautifully logical rules of chemistry. You now know the alphabet of atoms, the vocabulary of molecules, and the strict grammatical rules of chemical equations. The universe is incredibly understandable once you learn how to read it. I hope you enjoyed this explainer. So if chemistry is really just a strict, predictable language, what unseen chemical reactions are you going to decode next?